We will see some things from the world of NoSQL databases. Some of the slides, or of the first slides, have been shown already 2 weeks ago, but I think it's maybe a good repetition, and I can give additional comments on some of this. But before we start with the matter of this lecture, please observe some organizational notes. So currently, I think you are invited by Tom Online to participate in the evaluation. This is open between June 5th and the 20th. So we are asked to provide time for this, and that you can fill in this evaluation form. Please bring a mobile device next week. So then we will do this next week. Yes, and then we reserve 50 minutes of the lecture to complete this service. Okay, so this is here then this lecture code. Okay. The other thing is actually, here let me repeat this, that the exam is on Friday, July 20th, 1 to 3. Yes, so far we did not hear about any time clashes, but of course if you have problems, please tell us as soon as possible, because it gets more and more difficult to reschedule. Okay, this will take place in this Interimshörsaal 2. That's these flat buildings right next to the tube exit. Okay, so far 27 students have registered. Yes, please also keep in mind that this may be the last semester where this lecture is given. So because the study plan changed and it was removed from the mandatory curriculum, and so far it's not clear at all if there will be another run next summer. So if you're undecided, should you try it now, it means in your 4th semester, or maybe in 1 year in your 6th semester, then you may run into a problem. So far the examination board did not decide if it's going to be offered next year or not, or what would be the replacement. Okay, and the other thing is, next week we will have a guest lecture by Professor Ross talking about predict protein. This will not be the full slot, but he more or less will give you an introduction of 1 hour in the history and the current state of predict protein. Why is this important? Because this will give you an idea how scientific software is still developed and how scientific software still looks today, and that's quite different from the way you would construct a commercial product, where it's like, hey, you have a clear audience, a clear custom population, you define the needs of these customs, and then you actually make a targeted development. But actually that's the other way around. You have various tools, very specialized tools all over there, and then at some point you want to integrate them under the same framework, and challenges and also possible consequences from this approach will be then presented. Okay, so let's start with a short recapitulation of SQL, or some features of SQL databases. First of all, this SQL, or it would be more correct to say relational databases, but since SQL is the query language for relational databases, I use this more or less synonymously. They have a schema, so that means you have a defined set of tables or relations, and these relations have a defined layout. Okay, so tables, and actually this is already predefined and it's somehow engraved in the database. You have type data, so that means you have to predefine the type of every data. This actually leads to to the fact that everything is under control and everything is defined, and you know exactly already long before you add your data to the database how much space it would need on the database and how or where it could be found then. Means that's the advantage, that the space consumption is computable, and to some extent you can guess or you can calculate actually where some data might be on your hard disk. Okay, so we have this well-defined theory, which is actually also can be seen in the SQL query language. This is based on this relational algebra, and most of these databases all follow this ACID principle. So if you have no idea what ACID means at all, you should actually look this up. So because this is a very principal thing, and you will see this also then in contrast to the NoSQL database, where we actually relax some of these conditions. So that means atomicity, that some modifications are not interruptible. Consistency, the data are always consistent, they are independent, so interactions do not influence each other. And durability, whatever you do is then written on the disk, and if you switch off the machine, it's not lost. Yes. So we have the standardized query language, and typically we use indexes to speed up the access. And that's the reason, or actually it's not really clear if this is the reason why it's so good developed by software vendors, or is this true because it's so good supported by software vendors. Okay, then NoSQL is not exactly the opposite, but actually more or less a lot of else things. So the ideas have been around for a long time, so started in 78. It means long before the advent of the internet, but the big push came with the Web 2.0 in the 2000s, and together with this big table database on the MapReduce paradigm. Actually, typically you use nowadays NoSQL databases for terabyte and petabyte data. Actually, also relational databases have grown up, but we see also some problems with databases or with relational databases storing these amounts of data. And that's actually one of the reasons, or that's the reason they have problems to store it on commodity hardware. So what is the big difference? First of all, there is no model. You have sometimes model-like structures or very, very simple models, but we have no relational model. So it means the data, if you would print them out, have no table-like structure on the paper. So it's quite flexible. One advantage, as I said here, it's quite difficult to extend relational databases on commodity hardware. Commodity hardware means that the things you can typically buy on your own, but these here, for example, these NoSQL databases are much easier to spread on computers. What is the difference? There are two types of scalability. Is it covered? Two types of scalability, horizontal and vertical. Vertical scalability means we simply increase the memory of the machine. And you already know, or I think you know because you already spent some time in the field of computer science, there is a limit how much memory and how much disk you can put into one machine. That's horizontal scalability, and as soon as maybe table gets too big to be stored on one disk, you run really into issues with relational databases which want to fulfill these ACID principles, because consistency really becomes an issue. Okay, so most of them are open source. That's I think also one side of the medal. A lot of this is, I think, not really experimental, but started experimental projects, and is still not so kept under commercial control, like many relational databases from commercial vendors. Yeah, we have no or very simple schemas. That actually goes together with the horizontal scalability. The simple data replication is quite easy. If you want to run the database on many small or intermediate sized computers, of course it should be easy to propagate the data and copy this to the other machines. It wouldn't make sense if this is super complicated and it takes much time that you replicate your data between single nodes, because then this would suffer horizontal scalability. Horizontal scalability would say, okay, if it doesn't fit on one computer, you just put another computer right next to it and then it works again. This means adding simply more computers. Okay. Simple API depends if you see this as an advantage or disadvantage, and many different consistency models. So if you see the ACID principle as one end of the scala, then actually no consistency. You do not care if your data is consistent at all. This would be the other extreme, and the NoSQL databases are typically somewhere in between these resources. So I already mentioned this, or this is actually could be derived from the initial point. So if the schema is bad, then yeah, the query is also bad. Means here it's not really performant. So it simply takes a lot of time if you have to do some joins, if you forget to create important indices, and so on and so on. Most of this is defined by strings, and this is susceptible for typos. So once you, or if you change maybe the attribute name or whatever else, then it doesn't work like expected. Yeah, typically you maybe get only errors when you execute the query, but not when you author it. And it's really hard to modify this once you set up the database and start with this. So, and there are different types of NoSQL databases which actually have different approaches to solve this issue. So this column stores, document stores, key value stores, and graph databases. The first thing is actually key value store. It's a super simple model. We simply have a key and a value, and the value can be complex again. So this means actually you can create if you would encounter this without knowing about NoSQL databases, maybe in code or whatever, you could actually simply also see this as a set of nested dictionaries. What is the advantage? Actually, if you keep this in main memory, this is super efficient because you only store the information in the fields you have. So you don't waste space for optional attributes like in a relational database where you have to reserve the space. Okay. Yes, and so the values can be actually, yeah, again, hashes, sets, or lists, so you can create some nested structures. Of course, if you then write this to a disk, then it becomes already maybe less performant, but under certain circumstances, this might have some advantages. Since there is very little structure, the API is very limited. Maybe you can return the value of a key, but then you have to actually analyze the key and see, okay, what type is the value, what maybe subsequent keys or fields are there, and then you can traverse through this structure. But this is very, involves a lot of manual interaction. Then another or a more important family are the column families. So here it's actually relational databases are row families, column families. So what is the advantage? If you store the attributes column-wise, or think about that you want to calculate averages over some numerical attributes or whatever else, then because you store the columns together, it's very efficient to access the the values of all tuples, and you can omit all the items which have no value for this. So this is very efficient under this, and you don't have to waste space for not available values. In the relational database, you actually have this table, and if maybe 19 out of 20 attributes are not set, you still consume the space on the disk. Okay, so that means that the access to the columns is quite efficient, and this can be an advantage sometimes. So a more important thing, which we will see later in more detail, are so-called document stores. So the documents are not the Word-like documents, but this has a structure where you have maybe keywords, and you have text fields, or you have nested documents. So you can create already some kind of structure. If you have the same fields, for example, you can have something like you can create something like an index and so on. There are different things. Very popular is JSON and RDF, and also YAML as more or less rules to how to construct like such a structure. Okay, and another thing is graph databases. Graph databases actually is not so much about the actual storage on the disk, but how you represent the data and how you can integrate the data. And with graph databases, we consider that the data is represented as sets of nodes and edges. So you have a graph or a tree-like structure, and items are reflected as nodes, and then the edges reflect interactions between the nodes, and this allows quite intuitive analysis of relationships between the data. You could also do this in a relational database, but then you would have to write a lot of join queries and so on, and here is actually it's the ease of handling and the ease of access of the data. It's very suitable for traversing. Okay, so these are the databases. What other important concepts exists in the world of NoSQL database? First of all, this MapReduce paradigm, that's a way how to access and how to analyze this data. Then the cut theorem, this is actually a kind of completion, or you could also say some kind of precondition to understand the ACID principles. Then methods how to avoid problems arising from NoSQL databases and keep consistency, like the consistent hashing, multi-version, concurrency control, vector clocks, and so on. Okay, first of all, MapReduce paradigm, or actually it's not just a paradigm, it's a whole framework. It means to apply MapReduce, you typically need a software library which performs the different steps, the mapping step and the reduce step. And this was designed for the effect handling of data in the order of tera or petabytes, developed by Google and patented since 2010. So it comes from originally from functional programming, and it allows parallel processing. A few words about functional programming. In functional programming, everything is actually executed in a function. If you want to forward information or return values, you do this via parameters and a function call or return values. So you don't have actually local or global variables which can then be modified, or where you have to think about concurrency problems like you have in imperative programs. So this allows, or because it has no side effects, this allows for easy parallel processing. If you, I think all of you know already thread programming in Java. If you program in Java and if you share variables, then you have to be really very careful not to mess up the state of these variables. And since we don't have this type of variables, this is quite easy. And this allows to spread the work or the analysis on many nodes. If you have maybe a data set of 1 terabyte and your machines have only maybe 20 gigabytes of main memory, you could either do everything chunk by chunk, maybe load in the first chunk, analyze it, store the result somewhere, then load the next chunk, but this is maybe a very slow process. But if you could then in one step spread this whole data on maybe, what's it, 20 onto 50 machines, then actually they would process this in parallel, and it's an immense speed up. Okay, so no deadlocks, because we don't have threads which reserve or has to claim locks or whatever else. Yeah, no race conditions, and the internal data structure is not altered. So that means this makes it quite easy and quite quick, and we don't have to spend a lot of time worrying about all these nasty things. What is maybe a small advantage, since the data is actually, or the forwarded values of the parameters are stored on the stack, we have a slightly increased memory consumption on the stack, because we get a new copy on every level. Okay, so how does it actually forms? We have a set of transformation definitions. We don't need control structure, and we can even do this recursively. And arguments can be used as arguments or return values. So this is maybe new for you if you haven't maybe used Python or real functional programming languages before. I think we will see this later in an example. This is a very useful feature. In principle, you have two steps or two functions: a map function and a reduce function, and these two are used alternating way. So that means in the first step, for example, we want to do a word count on a very large text corpus. Then we have a map function which simply for every chunk, say if you have a word, then this occurs once, then we return a tuple of the word and account 1. And this is all returned, and then the reducer function simply sums up, okay, takes all the same keys, whereas the same word, and adds up the numbers, and this can be done stepwise. Okay, so this map function is applied to all elements of a list and returns a modified list of these key value pairs. And then the reduce step simply aggregates these return values from the maps into one result. This does not have to happen in one step. You can also have maybe one map step, one reduce step, another map step, and another reduce step. Okay, so what do you need for this? Actually, you have to create this map function and the reduce function, and then the framework provides this parallelization and the distribution to the node. A very big advantage is actually that the framework controls all this error handling. If you think about our Google, and you have maybe in one center maybe 10,000 computers, and they typically use commodity hardware, then it's very likely that any computer can fail, or you have maybe 2 or 3 or 4 broken machines every time, and you don't want to do this error handling by hand. So that means, okay, you have to check which chunk of the task did not complete because the machine broke. Then you have to reschedule this again, and this is everything done by the framework. So the machine actually the framework is responsible that everything is processed, and if some things fail for whatever reasons, it's automatically restarted. And of course, it also gives you information about the scheduling. So here is an example. For example, for this word count, the key is a document name, and the value is a document store. And then for each word W in the value in this document, we return such a tuple, means this word occurs once, and then in the second step the reduce function simply searches for the same keys and then iterates of the values and sums up the keys. For each v in values, this is parsed, and then finally actually it converts this again into a string, or this is could also be the number that it returns this key of the word and the aggregation of the numbers as the total number of these words in the document. Okay, how does this look like? Yeah, you can run this on commodity hardware. You can even install MapReduce on your own laptop and run it in a standalone mode. You can also maybe create virtual machines on your machine and then have it distributed, okay, but this doesn't really give you a lot of performance increase. It uses Ethernet framework, and this is suitable for really large clusters, so more than 100. You can also do this in more than 1,000. Of course, it's not, this is a very high level approach. You need also some underlying layers, so you have a distributed file system, so that means the data you want to process is actually stored on many different computers. Again, this gives you the chance to introduce some redundancy. So if you have a Hadoop file system, this every single piece of information is typically stored at least 2 or 3 times. So that means if one machine fails, it doesn't matter actually, because you have safety copies, and the system reschedules to recreate the third copy, and everything is quite stable. Yeah, you distribute your data over the different nodes, and then you only process this local chunk of the information. This is the big advantage. You don't have to copy a lot of data over the network, but actually you only have to import this once in this distributed file system. You may, let's get back to this 1 terabyte of data, and you have maybe hard disks of 20 gigabytes. Okay, that's nowadays not true anymore, but then you simply can, you have 100 computers, then every computer gets a chunk of 50, and you'd say, okay, but 100 times 50, then we would have maybe more, but this includes some kind of redundancy. So that means you cut this large data, input data into pieces, you store them on the cluster, and then you only analyze with these 2 functions here, with this map and the reduce function, you only analyze the local piece of the data, and then you only return the results to a master node, which then simply adds up over this 100 nodes, and this is of course much less data than if it would have to go over the whole data file. Okay, so this is about how the MapReduce framework and some ideas. Now let's come to a very important theorem, the CAP theorem, and eventually consistent. So we had already ACID, and the CAP theorem now says, okay, that actually horizontal scaling of relational databases is insufficient, because too much time, it takes too much time to extend this database to other computers, because this is frequently modified. Yes, okay, yeah. And then you always have to change the source code. Okay, so here is the CAP theorem, yes. Okay, so this horizontal scaling is difficult, and that's one of the explanations. First of all, or in short words, it says you cannot have the cake and eat it. So it means consistency, availability, and partition tolerance cannot completely satisfied at the same time. Only 2 of these criteria can be satisfied. What does it mean? For example, consistency, that all the data are consistent. That means, or think about you split a table in to 2 hard disks, and you start to delete rows on one thing, and you have to update your index, or you want to insert something in the table, then you have to rework the structure of the whole table until it's everything, and you have to coordinate this between the 2 disks, and this is very time consuming. So this takes time. The other thing is availability. You want a quick response time. Availability is quick response time, but if you, for example, just have to propagate changes over hard disks, the system is not responsive anymore. And the other thing is partition tolerance, means what happens if one of the node breaks, or network failures, hardware failures. So, because if you have the data on several nodes, on several computers, it can happen that one computer becomes unavailable. What do you do in this moment? And this is, and all these 3 criteria cannot be satisfied or completely satisfied at the same time. Typically, we only have 2 of this, and for NoSQL databases, the emphasis is on availability and partition tolerance. So that means we give up somehow this consistency, and we live that some data are not 100% consistent during the operation. Of course, here, or on the other hand, the relational databases, they stress consistency. That's, I think, maybe also the reason why it's used, for example, so often in financial or economical purposes. But this sometimes then on the cost of availability or partition tolerance. So if you have a hardware failure in a relational database system, it really takes a lot of time to rebuild the system and to back up maybe from disk or recalculate some of this data. Yes, and or if you have this on many disks, and if you have to propagate changes, then the availability is severely reduced. Okay, so here's a more concise definition of consistency. That means after database, after a transactional database should be consistent, that all of the different pieces of information are correct. And if you replicate the nodes, that means if you have in several nodes, all nodes should have the same state. That means that wherever you access a node, you should get the same node back, because there's also one thing, if you have your system distributed over a large area, like maybe Europe and the US, and many people want to access it, some people are closer in Europe, they access maybe nodes in Europe, others access the nodes in the US, and all of them should get the same result. And this is, of course, if you think about Facebook, it's not always guaranteed. If one friend of yours is currently on holiday in South America and he posts a question, or he posts something new, you don't want to wait maybe half an hour until this change is propagated and you see it, because you want to exit it immediately. Okay. Yeah, so this is the availability. We want a quick response. One thing, for example, Amazon. Amazon is a worldwide operating company. Anytime people add new items or other items run out of stock, you want to access this, but you want a quick response time. That means if this update would, or if they would insist on consistency, after every single change somewhere on the world, they would have to make a kind of freeze until this change is propagated to all of the nodes, and within during this time, people could not actually continue with their shopping. And of course, we don't want this. And then here maybe you miss one very recent offer, but you would not notice at all, and you go on. And this is, I think, much more important for Amazon, that the people can go on and experience a good responsive time than absolute consistency. Because if it doesn't work, if they say, okay, yeah, you have to wait 10 minutes until you get really the latest offer, because in 10 minutes you already left this page and you are looking for something else. Okay, so that means typically they try to guarantee a response time. Okay, and partition tolerance, it means the system even continues if one part of the system fails. So that means if you have maybe 2 or 3 copies of the same data, you can afford to lose one of this, but of course then it takes time to copy the data to and through the nodes and recreate maybe upon failures, and during this time the system is not completely consistent. But of course it doesn't survive. It does survive. Okay, so that means we come to reduced consistency models. So there are these base consistency models, means basically available. So that means you, within a certain limit, you typically get an answer. It's very consistent, but it's not completely consistent if you would let the system sit. So that means we have no changes, no interactions, then finally it would be consistent again. Okay, so we focus on availability and we sacrifice consistency. This is an optimistic thing, that it's okay if we wait long enough, then the system become consistent again, but we do not actually really require it. Okay, and this model actually is interpreted differently between different database systems. So some vendors are more consistent, some systems than others. Actually, you can also have this with the complete ACID model, but then you run into the problems described, or you have a very low level of consistency, then you run into other problems. Here, consistency, or keeping your data consistent, is actually transferred to the level of the developer, and you have to take care that it still works and makes sense. So these are 5 different levels. So that means causal consistency, read-your-write consistency, session consistency, monotonic read consistency, and monotonic write consistency. So this is the highest level, and this actually only means, okay, if one node writes something, the next time you write, okay, you at least see what you have written or modified before. Monotonic read means you always read the same things. Okay, how do you achieve consistency? First of all, there is these consistent hashing things that you actually use hash functions to calculate the hashes of the elements you store, and you map the elements of a very large source set to a very small set, and it means you can, in quite short time, you can determine if something has changed, and you can find it due to the structure of the hash. The advantage is has constant time, and you know hashings for checksums, and this can help you to detect manipulations. Here actually it's a quick way to find a constant place for memory. So we use actually this hash sum as a kind of path to the place on the disk, and we don't really have to sort the objects, and we use it to find it quick and to minimize the time upon insertions and removal of the nodes. Okay, typically they use a kind of circular hash space, so there's only a limited number, and if this would be exceeded, then we start with the small things again, so that means all the available space is recycled. Okay, this is a quite simple model. What is more sophisticated is the multi-version concurrency control. That means the data objects get versions, and versions change with time, or they represent a timeline. And every write access creates a new version. Of course, reading doesn't modify the data, and the objects, they also have references to the last recent version. And then that's a way to detect conflicts, and again here it's not then the task of the database to keep the data consistent, but it's your task of developer to determine, okay, do I care about this conflict or not? Conflict can be that you just lose one version or some data is inconsistent, or is okay, now I have to do it manually, because this is somehow based on the hope that conflicts that matter occur not so often, and I only have to execute this resolution code when it really happens, and I don't have to do it always when it's not necessary. Okay, why would you do no conventional logs? For example, you could log a table if you read it or if you write it, but then the whole table is logged, and if even if you would modify the table at different places, the first one logs it for everybody else, and all the other processes would have to wait until this first log is removed, and this causes a long cache pipeline or a lot of traffic network. And this is actually, its communication is really can be an issue in distributed systems. So it means we have no parallel access. So okay. So here is a model of this multiple view control. Okay. Of the multi-version concurrency control, and I think I will explain this in detail after the break of 10 minutes. So we continue 10:30. Okay, let's continue with this demonstration about this multi-version concurrency control protocol. Actually, the reason is not to prevent conflicts, but in case you have conflicting versions of an object, of a data item, how can you detect this? So here the arrow represents the flow of time, and we have Alice and Bob as acting processes. And this is here now how it actually works, that in the case of no conflict. So first of all, here this item has a version 0. So that's the starting version at T0. Then Bob reads the version 0, Alice reads the version 0. Since no writing takes place, actually, Alice does not overwrite this. But he can read again, one from the version 0 is still version 0, and at this time point here, transaction actually completed, and then here reads again after, so Alice writes, the version is updated, he reads again, and the transaction is completed, and then in the next read access he would read or get the version 1. So if this is then here completed and updated. So that means since here exists only read access, he misses here this last regional version, but no information from Bob is lost. So Bob reads and reads and reads, while Alice updates this item, and at a certain point this is then here in the system, and then okay, he reads a different version, he reads an updated version, but at least this is consistent. So the problem is now if Alice and Bob want to write. So here they both read again, and then Alice tries to update this and creates this version 1a, and now Bob also updated this and creates version 1b, and now it realizes that actually his last version was v0, but now the last version is 1A. And they realize, okay, meanwhile the data has changed and there is a conflict. So, and then it's up to the system to decide which version to keep from this, or if they completely roll back and say, okay, let's start again, and then maybe with a kind of random waiting period, Alice and Bob have to try again. So it's not about to prevent conflicts, but to notice conflicts, if conflicts arise. So here, only one writing, and there is no information lost, of course. If Bob would read here or could read this already, he got access to this updated version a little bit earlier, but this is not so difficult because finally everything is consistent. But here actually we don't know exactly which version persists. If it is version from A created by Alice or version from B created by Bob. So yeah, that's this thing here in this transaction, and so typically the system would say, okay, something is going on, the timestamps does not match, and yes, something happened. Okay, another way to deal with these things is vector clocks. The challenge is that many instances write different data at the same time, and they have to be somehow synchronized and ordered afterwards. And one solution is this vector clock. This is a vector clock process invented by Leslie Lamport. I think Leslie Lamport is better known for the creation of LaTeX, but he also worked in this field of computer science because he originated actually from operating systems. So there are two types of weak consistency criterion. That means if E1 causes E2, then the timestamp of E1 has to be smaller than that of E2, and the strong consistency criterion is the opposite. If E1 is smaller than the one of E2, then E1 has been the cause of E2. So of course, this does not necessarily, so that means whenever E1 has caused E2, then the timestamp of E1 is smaller than E2, but E1 and E2 could also happen more or less accidentally in this order, and E1 is not the cause of E2. On the other hand, say, okay, if E1 is smaller, then this is of course a much stronger statement. Yes. Okay, and then if you have different timestamps, then the events can be sorted in a partial order. Yes, of course, this timestamp does not need to be the real time, because then it depends on maybe your speed of the computers. If you count in seconds, milliseconds, nanoseconds, whatever else, and so on. The only thing is that it's a kind of monotone increasing integers, and the timestamps fulfill only the weak criterion. So that means we can only say, okay, if they have a causal relationship, then timestamp of E2 is larger than timestamp of E1. So, first of all, what do we have? So we have a version vector. This is a tuple of values of timestamps, and means in these timestamps every clock is a counter which is incremented, and every process remember the sender and the timestamp. So that means we can have this in the example in a second. So actually this vector clock is a combination of an ID and the time tuples from this sender. And this enables the client to sort and to figure out different versions when multiple clients update and replicate records at the same time. So you actually can see that this is. So we have an example where it's okay, we have 4 people and they want to figure out what sports to do. Okay. And they want to agree on this. So how could such a 4 people? Yeah, okay, 3. Okay, so These are our three actors. So we have Anna, Paul, and Laura. So, of course, first of all, Laura starts the discussion, says, okay, I want to go jogging, and sends this message to Paul and Anna. Okay, and attaches her timestamp. So L for Laura and 1 her internal clock to this. Okay, so Paul receives this, or no, Paul says he wants to go surfing, and he sends this to Laura and to Anna. So here he knows already about the timestamp of Laura, it's L1, and he attaches his own timestamp P1 to this message. Okay, so that means Laura knows that Paul knows about her suggestion, but he sends something back. Okay, that's easy. Okay, and she says, okay, let's go surfing. She agrees. So that means she updates her timestamp to 2. Paul is still 1. That she includes, and then so far we mention here only the ones which have already a value. Laura does not receive anything from Anna. Doesn't know. That's why the count from Anna is still set to 0. So this message here got lost. So Anna never got this surfing message from Paul, and Anna agrees to the suggestion from Laura. Yeah, okay, let's go jogging. And then it's okay, that's the timestamp A. She attaches A for A1, their own hand, and this is response, and for Laura 1. Okay. Then we have here actually 2 conflicting things. So jogging would say, okay, jogging Anna 1, Laura 1, Paul 0, and surfing. Also Paul gets here 2 conflicting messages. Here is Anna's time clock missing, here is Paul, and they're inconsistent. And that's how actually now it's actually a decision of the system. What Paul says, okay, then Paul can decide actually, okay, I want to do surfing, and he updates its counter to 2 because he already has actually counter 1. Okay, now it's my counter is 2. He received Anna 1 and Laura 2, so that's the latest version of the counters of the 3 things, and sends this to the 2 others, and then now all the 3s are consistent. So Anna knows surfing because this P2 A1 L2 is consistent with or means it's after this A1 L1, and it's also consistent here because P2 A1 L2 is after this here. But here you cannot clearly say, okay, which is a consequence of the other. Okay, so this is how you can use these vector clocks to resolve these issues, or at least first to detect these issues, and then how you resolve it, it's up to you. Okay, so this is the longer story. For this I will not actually repeat this. Okay, so another thing is in this cluster there was this kind of action where you have maybe different roles. Okay, one start to query or make suggestions to the colleagues and so on. Here I only will skip this briefly. This is actually to get your rough ideas, but don't care about the details. There are so-called quorum sensing algorithms where you have a kind of poll in a set of nodes which then the nodes actually vote which version of the data they want to accept. Of course, if you have a wall or election, yeah, you need some kind of organizers, and that's that's realized with a few special roles. So, what are the advantages? You can afford that nodes fails and that transaction crashes or messages are lost. So first of all, one client suggests the values, and then this has to be accepted by the others. If you meet a quorum, then it's accepted, and for each of this ballots you have a leader. That means it's one who says, okay, let's vote about this now, and so on. Okay. Yeah. Okay. So now this was the theory. Now let's theory about this conflict detection and how can you synchronize many nodes. Actually, this is a very complex and very important field, but I think for us in our function as user of the systems, we don't really have to care about all these details. Let's talk about graph databases. First of all, the graph databases allows to represent connected information very intuitively with vertices and edges, and actually this is used in a lot of cases. So for example, internet routing, contacts in social networks. You can also use this for recommender systems, fraud detections, and so on and so on. I think one very important thing in bioinformatics is that gene regulation is a network, because typically you have a regulator gene and a regulated genes. You can have maybe recurrent regulations, so that means feed forward or backward loops. Yes, or you can also model metabolic pathways by using graphs where maybe then the direction of the graphs indicate the transformations of several substances, and the nodes are maybe intermediate products, or you could also use this as enzymes. Okay, so to work with graphs you need a little bit of graph specific language. So here the graphs are represented by a pair of two sets. We have the vertices sets and the edges sets. So vertices are also called nodes. This is a kind of fact or piece of information, and then the edges are the connections between this, and they represent the relations between these facts or these vertices, and can be directed or unidirected. So I think this is here the formal thing, that a graph is a tuple of V and E, and V could be a set of 1 and 2, and E actually it's a relationship, means it's like a cross product of V and V, because every node can be connected with every node. Since we only have 2 nodes, we only have 1 edge in the set. But of course it's quite easy to see if you have a fully connected graph, then the number of edges would grow exponentially in terms of the linear growth of V. Okay, so for the databases we use a special type of graph representation, the property graph model. So this is a directed but multi-relational graph, so we can have many different relationships in the graph, and we have labeled or typed edges, and you can also attach properties to vertices and labels. And the property is simply a key value pair of the type string and object, like for example Alice or name Alice or age 30. So that means that's the key, that's the value. Okay. Depending on the database system, you can have a strong typing, so it means you can really define types of the edge, and so increase some kind of strict a strict modeling. This is useful to model a semantic meaning, so that means a connection between two facts really have a meaning. So for example, if you say, okay, means for gene regulation, it's not only that one gene somehow regulates another, but you can have, for example, upregulation or downregulation or is regulation. Then this gives you already much more information than simply the fact that two genes would somehow interact. Of course, this allows you to then define criteria for consistencies and easy indices, and this makes the partitioning of graphs easier. Okay, bidirectional edges in this property graph model are typically realized by unidirectional edges. Okay. Multi-edges require different labels, and vertices and edges have a unique identity. So that means, of course, we have to address specifically all the items, the nodes, and the edges, and then that's why they have IDs. Multi-edge is an edge which connects more than one node. Okay. So for the IDs, you can use anything: integer, strings, URIs, whatever else, and some models even support multi-value property, which allow lists or sets of values. Okay. Of course, you can also have special meaning of the values, so like edge weights, yes, higher order relations, hyper edges or hyper vertices. So hyper edges are edges which connect more than one node. Okay. So here's an example of such a model. For example, here this item 1 or vertex node 1, node 2, node 3, node 4. Node 1 has the type person with the value Alice and age 20. Node 2 is also of type person and name Bob and 25. And then they have this relationship or this edge between knows, that's the label, okay, and a date. So this is a property that is like, okay, Alice knows Bob since June 2013. Of course, you can also have the connection here that Alice knows Paula. You can also have here, this is another node, ID4, but it's a different group. So this is the chess group node, and then the relationship is here that Paula is a member of this group, and the group has the member Paula, and so you can also model these relationships. Okay, what are actually possible extensions? So for example, we have this higher order relationships with hyper edges, connect more than two nodes, but we also have higher vertices, and this is a combination or a set of vertices and nodes with internal edges. And a path is a sequence of edges connecting several nodes. Subgraph is simply a connected or defined combination of nodes and edges into a single node. And yes, okay. So how can we represent this? Because, okay, this is a nice model. You can easily draw it on paper and annotate this. It's very nice, but actually, at some point, if you want to have a graph database, you need to implement it or to code it somehow. There are different representations in memory, and they perform differently. So typically this depends a little bit on the data and on the usage, what is the best representation and the best support for a variety of algorithms. So first of all, this is, I think, one of the oldest or simplest formats, the adjacency matrix. It's a square matrix and table, and the nodes and nodes are listed horizontally and vertical, and if a node exists between these nodes u and v, there is in this table at position u and v a value. So you can also then use different values to reflect direction of the edges, of course. Yes, but that means that the test for the connection can be done very quick. So you simply go there and see, okay. But on the other hand, if the graph is sparse, you have to go through the whole row or through the whole column, and if you want to search for all maybe partners of node U, you have to go through the whole row or column of U, and if the node is sparse connected, it's a waste of space, or you have a lot of empty cells in this table. Is this clear for everybody? Why for sparse connected graphs, adjacency matrix is very space consuming? Okay, imagine if you maybe have a graph consisting of 1, 2, 3, 4, 5. So okay, it's actually a very simple graph, and then you would have a table of 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So okay, and let's see. Okay, only one is connected only to 2. 2 is only connected to 3. 3 is connected to 4, and 4 is connected to 5, and 5 is connected to 4. If we don't use only one diagonal, and you see. There's a lot of space around the really needed cells, and this is the thing why it's so inefficient in space. If the graph is sparse, of course, if every node is connected with everything, yeah, you need this space. Okay, so yeah, huge space consumption with sparse matrices, and if you want to identify all the nodes from one node, you have to go through the whole column or through the whole row. You cannot represent hypernodes because yeah, you have only here one value, but you cannot see that maybe one edge connects more than 2 edges. Okay, next step is the incidency matrix. This is slightly different, and here we have on one side the nodes of the square, of the rectangle, and on the other axis we have the edges. And this is a more efficient way to store a weakly connected graphs, because yeah, and in more connected graphs, it needs more space than adjacency matrix. The advantage here, you can represent hypergraphs, yes, but of course you see already, yeah, you have to know about the problem to guess this is okay. Then a different thing is the edge list. So you have a set of edges and a set of nodes, and you keep this separately, and yeah, whenever you introduce an edge, yeah, this is very easy because you only have to go through the edge list and remove this or not. So that means the edges know which nodes they are connect. But of course then traversing the graph or identify the connection edges giving a node is inefficient because you always have to go through the whole list of edges. An improvement of this is the adjacency list. So here the edges are sorted according to the start node, so you don't have to go to the whole list of edges, but if you know or in which node you're interested, you can get quite fast to the outgoing edges from this node and then retrieve them. Okay. And then the time consumption depends only on the connectivity of this node and not on the graph size. So here we have a few examples for this. So this is the graph. This here is the adjacency matrix. We see here actually this V3. It's V3 to V1, V3 to V1. Yeah, okay. So we have two edges here from V1 to V3. Yeah. So this is an example of the incidency matrix. So you did the nodes here on one axis, the edges here on the other. We can also use this to indicate the directions. And this here is then the edge list, where you simply have the nodes, and then or according to the nodes, all the edges. So we have from node 1 we have an edge to V2, we have an edge to V3, and where to V3? V3, yes, and we have a second edge to V3. Okay. Okay. So then, what can you do with graphs? So graphs, you want typically you make no select queries, but you want to find connections between different parts of the graph. That's what we call traverses, or it means outgoing or starting from a certain point. You want to maybe reach out to the neighborhood and find out about the neighborhood, or you want to find a certain other thing. So there are different search strategies. First of all, the most common ones, breadth first or depth first search. What the best strategy is to search the graph depends on your specific setting. In the breadth first search, in the first iteration, you determine all the immediate neighbors of your starting point. Then for these neighbors, you determine the next level of this first order neighbor and add it to the list of nodes you want to check. Then you look at the second immediate neighbor, and so on and so on. And you first iterate through all the immediate neighbors of a node, and then next round the neighbors of the neighbors, and then in the third round the neighbors of the neighbors of the neighbors. So this is actually keeps you close to the start point, to the start node, but of course you have a huge list of nodes you have to visit. Depth first follows a different approach. So you start with the first neighbor, and immediately, look for the neighbors of this first neighbor, and then visit the first neighbor of the neighbor, and then visit the first neighbor of the neighbor of the neighbor, and so on. And you try to go as far away from the start point as possible, and then once you maybe reach the border or the end of the graph, you go back, and then you first visit all the far away nodes, and then come back and start with closer nodes again. Okay. There are also other algorithmic traversals where you can implement any strategies, and this sounds maybe a little bit nonsense, but actually if the graphs are very huge and we say, okay, it doesn't care if a specific connection the graph does not really care, I want to get some general feeling about the graph, then you can have random based walks where you simply say, okay, let's walk a few steps in this direction and see what I encounter, then let's walk a little bit in the other direction, and so on. How you this exactly generate is up to you, but this already maybe gives you a good feeling about the neighborhood, especially if the neighborhood is very large. So, for example, if you want to maybe get some trends in maybe social networks, I think it's you don't have to completely search. So this breadth first, depth first, they search a graph completely, but if you maybe want to create a profile of a person, maybe you don't have to search all of the friends, but maybe a fraction of them would be already sufficient, and random search is then something like this. Okay, so you can add indices to the graphs. They are full first-class sentences in this database, and you can insert this as subgraphs attached to specific nodes or specific information. Yes, also even in graphs you can have indices allowing you very fast search. For example, if you want to follow only certain relationships or want to search only certain types of nodes. If the graphs is too big, it's quite easy to split them into partial graphs, but the optimal partitioning decision is highly domain and semantics depending, so yeah, that's something for the developer. Okay, so the theory of the graph is quite easy, but actually how this is realized in programs is not very well standardized. So there has been this Tinkerprop project. They tried to come up with a graph processing kind of standard. So yeah, the idea was to provide uniform interfaces to access property graph based models. Actually it does not really care about how this graph is actually stored. So this is if you then have your graph finally stored in a relation database or in another database, doesn't matter. So we actually leave this decision and this burden to the developer of the system, and this is even if this is maybe important for the performance, but this is so far away on this level. We are not interested in this. We simply look at the data as a graph. Okay. So yeah, here's some examples for this interface, and we use a Neo4j graph database. So actually Neo4j is a graph database. I think they also offer O'Reilly book about graph databases for free. They call it graph database, but it's about Neo4j. And they, for example, they simply store the data in a file. So they have a sophisticated file structure. They don't need like a MySQL server. So here it's file based, this example. So first of all, we create a new graph. So the graph is like the root in an XML or whatever the main contact point where everything is attached to. Then very easy, we create 3 vertices and add this vertex directly to yes. Okay, so this graph should create this vertex. So far the vertices are not connected, they have no properties. So then we can set the properties here, always name and Carol, and then we create the edges. And the edges actually introduces the connections or the relationship between the graphs. And this is at edge between E1. E1 is the name of the edge. And then between Alice and Bob, and that's the type of this relationship that knows each other. Okay. And then besides the type, we can also set a property to this edge then here. Okay, this edge has the property since. Yes, and once we're done, we they call it call shutdown, but this means actually save it to the disk and continue. So of course, once you imported all the data in the database, you can load it and then use it again. Okay, so here is a way how to generate an automatic index about this, and you want to create an index about the name property, create automatic index of name about this vertex class and index key. So that's a quite straightforward thing. You don't really have to worry how is this index created, how is it structured. This is already handled by the system. Okay, you can also re-index the things if you had nodes before. If you had new one, it's a good idea to re-index these indices because yeah, they should also be then present in the index. Okay, how can you use the index? For example, we want to iterate or over the index with the get name Alex, and then we print out the index, the vertices where the name matches. Okay, so this was our first attempt to standardize access to graph databases. The thing is, graph query languages are not really very well standardized. There are a few attempts. Sparkle means structured query language. Yeah, Sparkle and it's the RDF query language. Here you devise patterns. You can navigation based where you actually say, okay, go there, or logic based where you specify conditions, how to or what nodes you want to retrieve. That's OVL and graph log. But every graph database actually comes with its own thing, or they only implement a subset of this. So Neo4j, that's one of the examples in the exercise we will use, is one of the oldest NoSQL graph database since 2003. It supports full ACID support, so this is one of the examples which are here very close to the standard, and uses its own format to store the graphs on the disk. Okay, but for indexing they also use a third-party project, actually this Lucene library from Apache. You can embed this in your Java code, so that's directly loaded, or you can run this in a server that you can connect from different clients on. So this is here the integration by Maven. So you simply create here a new embedded graph database. You give the file name where it should write the information, and then you have this graph database service. Okay. So that's how it actually works. So you start a transaction, you create your node. So the transaction is this what makes it consistent. So either the complete transaction is executed and added to the graph or not, but you will not end up, for example, where that may be something, you have an interrupt here or failure, and you have created some nodes, but you did not maybe properly initialize the nodes or missed the edges you want to add to. Okay, that's you create the nodes and you set the properties yes to the nodes, and once you have configured your nodes, you create the relationships and so on and so on. It's a very straightforward process. Okay, and if the transaction fails, you get an exception, and again you can okay. Indexing is also quite easy. You simply call the index function, and then you can also iterate over the index's user, and yeah, then you can add also this user to the index. Alex get property by name and so on, and this you have a very easy interface. Okay, besides this traversals and the wildcard searches, there are a number of sophisticated tweaks. You can, in Neo4j, you can determine the search order. Okay, is it breadth first or depth first search? You can also handle, or you can define how you handle multiple hits of the same nodes. You can define pruning criteria. Okay, don't go into these regions of the graph. Of course, filters can be hits can be filtered and so on. Yeah, so here is an example for how you traverse this graph. So you say, okay, don't go further than depth 2, and then apply here the filter node. Okay, you filter only on the relationship nodes. So you don't have to actually do this on your own, but you can already include this that you only want to have relationships of type nodes. Yes, And then you simply iterate over this traversal description, and you only have here the hits, and you can then do something with the hits. Okay, so besides the Java, Neo4j comes with its own query language. So I think it's version 1.4, and this was originally developed for pattern recognition. It is declarative. Declarative means you don't have to write, okay, for X in maybe a set of nodes do this, but you say, okay, give me all nodes which have maybe which are child relationship or to a certain node and have properties and so on, and then the system resolves this for you and returns you the set of nodes or edges which, or actually it returns a subgraph which fulfills your constraints. So you give only the constraints and then the system solves this for you. It's implemented in Scala, so you can, since Scala is a functional language, you can easily parallelize this and run this on many computers if you have very large graphs. Okay. The query structure is as follows. So first you start a set of nodes, then you have a match statement, means which nodes you want to select, a node in parentheses or edges with this error, and then you have an return statement with optional where or sort. That means here you can set additional constraints. So here is an example. For example, we have start with person 1 and 2. We say, okay, we want to find all the matches where a person knows a friend, and then we impose additional restrictions. Okay, friends have to be, or the attribute of friend has to be larger than 18, and then we want to have actually the friend name, the friend age, and the friend city sorted by friend's name. Okay, or we can say, okay, we start on the person index and for Alice, and we want to know actually the friend of friends, and finally we only return the friend of friends. Okay, here we say, okay, well, the friend age is not below 17, also means 18 and more. This is 19 and more, this is 18 and more. Okay, so this was a very brief primer for Neo4j. You will see this more in the exercise, how you actually access this and how you write queries and how you interact with a graph database. So that's here one of the next points. So that actually interfacing with NoSQL database from a program is quite difficult, or not difficult, but the APIs vary heavily. So that means if you decide to change one database with the other, you mostly have to rewrite a lot of the code, of the interface code. So there is a minimum of functions the database should provide, and they most support the so-called RESTful interface. Or RESTful is the representational state transfer. So that's where REST comes from, representational state transfer, and this was invented for web application, and this defines a minimum set of protocols and some meaning of these functions, a minimum set of functions and the meaning of these functions. Yeah, we all know this from the HTTP protocol, but can be actually also used for databases. So actually it was described in 2000 by Roy Fielding. Okay, so what is this set of functions? Sometimes it's also called the CRUD or CRUD functions, and this is actually means create, read, update, and delete. So that's what these systems provide. It does nothing say, okay, actually how complex a create function is, how the actual syntax is, but at least you can create new items in the database or in the service, you can read this, you can update existing data, and you can lead this. So this is in SQL, this is represented with these 4 commands: insert, select, update, delete. In HTTP, it's post, get, put, or delete. So these are the specific implementations. This is the theory. Okay, so what do we need to do this? First of all, we need resources, means databases or services which do this, operations and links. And the idea is that each request is independent, it has no state and no need for synchronization. That means whenever you issue such a request, you don't have to be worried that you create some kind of inconsistency or whatever. That's the responsibility of the system. So you can look at this HTTP protocol as an abstract combination of nouns and verbs, and each request is defined by the application of a verb to noun and optional response. So that means you want to do something with, do something with something. Okay. So the request is composed of a header with a method and a metadata in the key value format and optional body, and we see this then in a second. The resources can be anything: HTML document, a video, a process, and typically you have maybe a URL or URI. This is quite abstract and depends on the system how it's represented. Okay, so the operations here in the HTTP are this get, head, put, post, on, delete. I think maybe put and delete is rarely implemented. Most web servers only implement maybe get, head, and put and post. Yes. So what are the characteristics of these operations? Operations can be characterized according to the criterion safety. Are they safe? Are they idempotent? And this is important for the system's integrity and some caching performance. First of all, I think safe is the best thing. It has no side effects and no responsibility for the user. What means idempotent? It has a side effect, but only for the first time. Upon multiple execution, the server state does not change anymore. Okay. So, for example, the get or the head method are safe and idempotent. So that means returns only meta information about the resource, and get returns in addition the whole thing you required. Okay, no problem, because the server just sends back the information, no change of the information, nothing can happen. For example, this is here a non-conforming example. Action equals delete, because delete would be change the state of the server, and this of course would not be a safe thing. So put means idempotent. You upload a resource, means it has no side effect. No, side effect. It has side effect because you upload this, but only upon the first execution. So that means once you uploaded this and you uploaded it twice or 3 times, it doesn't matter if you overwrite this or not. The state of the server does not change anymore upon the first upload. Okay. Okay, so here is a simple example. First of all, for example, the query, we have a query, get this document, then the response means return document in version 1 and document content. Then we modify this document and upload it. Okay, we return this, okay, yeah, we retrieve document 1. The server says, yes, that's the latest version, so I accept the modified thing and update the version to 2. If I would like to upload this again, then it would say, okay, no, but I have already version 2. I don't accept your upload. So then this is also a way to make it safe, and this here is still idempotent because the state of the server does not change anymore upon the first upload. Okay, so delete is also idempotent. It's not safe because of course it modifies the server, but once you have removed this item, you cannot remove it anymore, and yeah, if you call it fail or if it's say okay is no effect, I think that's the same in the end, but actually it's yeah, idempotent, and multiple executions of the same delete statement does not change the state of the server anymore. Okay, post is the most uncertain one, so makes no guarantees at all. So it may be that the state of the server stays the same upon the first execution, but it doesn't need. It can also be changed again and again and again, so you have to be more careful. And of course, since you upload data, it's not safe also. This is typically used for quite complex queries when you want to upload larger data than in the get method. Okay. HTTP itself does not support links, but in the theory there are also links in these other models. Links are modeled in URIs, and the encoding depends on the type of the representation. It can contain metadata to support appropriate resources by the user, but as we have seen in XML, the connections between these resources are very important. Okay. So here are some examples how this could look like in code. Here we have a kind of beverage library. So this would be here an item for ingredient for a cocktail, and we post this. That means we want to upload this to the database. So post, then HTTP1, the host to cocktailsexample.com. Okay. Here this content type means application JSON. That means we upload a description in JSON format. The JSON format is a very simple format. It's a key value thing. So everything is enclosed in curly braces. We have here a string as the key, and the value can be also a string, or it can be a nested document. So we see here ingredients, colon, and then new curly braces opens, and then this is here the curly braces more keys, so it means here, and then this is again a nested document where you have this lime and then some preparations and so on. So there is no limit how much combinations of this you can nest. So either here you have one value, or you have a composed value indicated by the curly braces. Okay, so we uploaded this thing. Now we want to have a get method. That means we return the get. So we have this ID1. I think this was the response state. So we upload this, was not there. This is the response. We created something with ID1 on the data. So, okay, then we have the get statement. We get back now here this ID. This was inserted by the server, the full thing, and we also have here some links added by the server. So it means that's how you can actually publish this, where you get it from, and this is how you can delete it. Okay. For the put thing, we want to update and add the text to this. Here it's an example for delete statement, and we then want to change the state publish equals true, and then we also have this changed links section, so we only can here have this delete and the ratings because it's published. Okay. So after the set of minimum operations, we will also have a look into document stores. So they originally was invented by Damien Katz and Lotus Notes. So this was one of the super earliest document stores. Actually, it's a kind of groupware server and now CouchDBs, and there are also a lot of others out there. We will have a look at MongoDB here in this thing. The responsibility for the schema is moved from the database towards the application, and that means we don't have to worry about normalization and referential integrity. So if some items are not there and we have a link, then it's not there and we don't care anymore. What is the advantage? So we are much more flexible. So we don't have mandatory, or typically we don't have mandatory items, and we can modify the schema on the run. So for example, if you start to create your own database where you put in abstracts for interesting research articles you read, that's very nice, but then maybe you also want to add your own manuscripts and you want to add some kind of reviewer notes, then you say, okay, you simply add the fields on as you need it, and you don't have to go back and say, okay, export this everything, reformat everything, re-import everything. You simply can add new fields where you need it, and you're very flexible. And if you realize, especially if you realize, okay, this was not maybe the best ideas, from now on you want to add more fields, then you can do this way. Okay, so MongoDB is a document store, as I mentioned here, and it's very close, or tries to close the gap between this classic relational database management systems and the key value stores. So key value stores, one key, maybe complex value, and here we have this strict table scheme, even if most of the fields are not present, and we waste a lot of space. And I think the advantage is also that this was supported by a number of successful internet companies. It comes with a very good integration, so you have adapters for C++, Java, JavaScript, Ruby, Perl, Python. We will see JavaScript later on. And I think this was the last slide of this. And I think with this very brief outlook in the world of document stores, I would like to close for today. We will continue with document stores and see more examples and demos next week. So next week we will continue with NoSQL databases. We will have this evaluation, so please bring your computer with you or other mobile device. And then I want to welcome Professor Rost to talk about Predict Protein, which is an internet server around since 1992, and this is maybe this next or beside the Aquaria talk, the second real world system talk, where you see, okay, that's all the theory and it's nice, but how does things look in reality? Thank you for your attention.